So I've said that if you have a vector field, a two-dimensional vector field with component functions p and q, that the divergence of this guy, the divergence of v, which is a scalar valued function of x and y, is by definition the partial derivative of p with respect to x plus the partial derivative of q with respect to y. And there's actually another notation for divergence that's kind of helpful for remembering the formula. And what it is you take this nabla symbol, that upside down triangle that we also use for the gradient, and imagine taking the dot product between that and your vector valued function. And as we did with the gradient, the loose mnemonic you have for this upside down triangle is you think of it as a vector full of partial differential operators. And that sounds fancy, but all it means is you kind of take this partial x, a thing that wants to take in a function and take its partial derivative, and that's its first component. And the second component is this partial y, a thing that wants to take in a function and take its partial derivative with respect to y. And, loosely, this isn't really a vector. These aren't numbers or functions or things like that, but it's something you can write down, and it'll be kind of helpful symbolically. And you imagine taking the dot product with that and, v, who has components, these scalar valued functions, p of xy and q of xy. And when you imagine doing this dot product, and you're kind of lining up terms, and the first one multiplied by the second, right, quote unquote multiplied, because in this case, when I say this first component multiplied by p, I really mean you're taking that partial derivative operator, partial x, and evaluating it at p. That's kind of what multiplication looks like in this case. So you take that, and as per the dot product, you then add what happens if you take this partial operator, this partial y, and quote unquote multiply it with q, which in the case of an operator means you kind of give it the function q and it's going to take its partial derivative. So we see we get the same thing over here. It's the same formula that we have, and it's just kind of a nice little, you could think of it as a mnemonic device for remembering what the divergence is. But another nice thing, this can apply to higher dimensional functions as well, right? If we have something that's, something that's a vector valued function, and it's going to be a three-dimensional vector field. So it's got x, y, and z as its inputs, and its output then also has to have 3 dimensions. So it might be like p, q, and r, and all of these are functions of x and y. So that's p of x and y, q, x, y, and z, right? So p of x, y, kind of got in the habit of 2 dimensions there. P of x, y, and z, q of x, y, and z, and then r of x, y, and z. And I haven't talked about 3-dimensional divergence, but if you take this and then you imagine doing your nabla dotted with the vector valued function, it can still make sense. And in this case, that nabla you're thinking of as having 3 different components, right? It's going to be, on the one hand, is partial x. I should say partial x there. Partial x. The second component is partial y. And the last component is partial z. And the ordering of the variables here, x, y, and z, is just whatever I have here. So even if they didn't have the names x, y, z, you kind of put them in the same order that they show up in your function. And when you imagine taking the dot product between this and your p as a function, q as a function, and r as a function, vector valued output, what you'd get, and I'll write it over here, is you take that partial x and kind of multiply it with p, which means you're really evaluating at p, so partial x here. Then you add partial y, and you're evaluating at q, because you're kind of imagining multiplying these second components, and then you'll add what happens when you multiply by these third components, where that's partial z by that last component. And, since I haven't talked about 3-dimensional vector fields or 3-dimensional divergence, this last term, maybe it's not a given that you'd have as strong an intuition for why this shows up in divergence as the other two, but it's actually quite similar. You're thinking about changes to the z component of a vector as the value z of the input, as you're kind of moving up and down in that direction changes. But this pattern will go for even higher dimensions that we can't visualize, 4, 5, 100, whatever you want. And that's what makes this notation here quite nice, is that it encapsulates that and gives a really compact way of describing this formula that has a simple pattern to it, but would otherwise kind of get out of hand to write. See you next video.